let's get the ball rolling. Today we're going to brush up on complex numbers. So that was our third test. We squeezed the 3 in before the end of term 1, so we did a good job. Alright, so we'll just get straight into it. We have 2 complex numbers. We've got the complex number 3 plus 2i. So the real component is positive 3. The imaginary component is positive 2. And we've got w, which is 1 take 4i. And we're asked to find R8 z plus w. So when we're adding complex numbers, we add the real components together. So we're going to have 3 plus 1. The real component is going to be positive 4. And then we add the imaginary components together. 2i plus negative 4i will be negative 2i. Alright? So the complex number z plus w is 4 take 2i. And I'll just reflect those on the argument plane here for you guys. So we have z is 3 plus 2i. Here's our real axis, here's our imaginary axis. 3 plus 2i, that's z. We have w is 1 take 4i. So that's w. And if we're doing z plus w, right, there's two ways we can think about it. But what we're doing is we're going to move that, we're going to translate it such that the tail of w meets the head of z. Alright, so that's going to be this one. And you can see it across 4 down 2. Alright, that it corresponds, or we can work it out mathematically. Alright, so we can make out this is a vector argument, right? And this is a algebraic argument. Okay, so let's move on to C then, because B is pretty similar. So in C, we have z times the conjugate of w. So for you to perform the conjugate, what that means is we're going to have 3 plus 2i. Z remains the same, but with w, the only thing we change is the symbol in the middle. So it goes from 1 take 4i to 1 plus 4i. And then we'll just FOIL that one. We're going to have 3 plus 12i plus 2i plus 8i squared. So that's 3 plus 14i plus I squared is minus 1. Alright, so it's 8 times minus 1, minus 8. So we're going to get minus 5 plus 14i. Alright, and we could sketch that one on the argument plane as well, but I think we're okay with this. Okay, let's move on to modulus and argument. So this flows on pretty well from vectors, especially when we're talking about the modulus. So modulus means how far does it go, what's the size of it. Find the modulus and argument of z equals minus 1 take 2i. Okay, so for the modulus, we're doing the square root of each component squared. Alright, so the modulus is going to be root 5. And for the argument, we will rely on our calculator. Let's see if I can remember these steps. Just because when we define an argument, right, we define it in radians from this point, okay, where we can go in positive. It's constrained, right, such that minus pi is less than b is less than pi. Less than what you should. That one's less than. That one's less than. Alright, so let's see if I can remember. So option, complex, argument, and then we input the thing we want to know the argument of. So I'm just going to put in brackets, what's the complex number? Minus 1. Take 2i. The I button is located where the 0 is on the calculator. And I've got minus 2.1. So this one's not that clear. It goes on infinitely, but we'll just keep it as that. That's the argument of the complex number. Minus 2.03. So what does that mean? We've gone 2.03 radians anti-clockwise. And we expect the complex number to be here, right? Because it's minus 1, take 2i. Minus 1, take 2i in that direction. All right. Question 3, we start talking about some loci and some regions. The first one is, on the argument plane, sketch the region such that the modulus of z is less than 2. All right, so here's our argument plane, and we're drawing a complex number from here. It could be in any direction. We haven't dictated which direction it's going in, but the constraint we have is that the modulus has to be less than 2. So if we draw some circle that has a radius of 2, all right, the complex number can occur anywhere in there, right? 2, that's probably 2, minus 2, minus 2. All right, the complex number can occur anywhere in there, but it does not exist on the line because it's less than 2. So I've indicated that with the dotted line. Then in the next one, we've got the real part of some complex number is larger than 3. Okay, so the real axis is the horizontal axis. Here is 3, and the real component has to be larger. We've got larger than we know, we've just got larger, so we'll draw a dotted line there for an asymptote. Has to be larger than 3, so it could be anywhere here. We haven't dictated the size of the imaginary component, so it could go up and down forever as well. Okay, then we're moving on to polar form. So we've got this complex number, z is root 2 cis pi on 3. State the modulus and argument. Okay, so the modulus is the number out the front. If nothing's written there, the modulus is 1, right? So the modulus of z, that's how we denote it. It's correct notation. Modulus of z is root 2. And the argument of z is pi on 4. Pi on 3. Okay, sketch it on the argument plane. So pi on 3 is like the unit circle, right? It's like the unit circle. Pi on 3, that's about here, and it has a length of root 2. So, if we somehow indicated that length as root 2, like that, that would be appropriate. Put the pi on 3 here, label the axes, real, imaginary. Wonderful. Okay, and then find in Cartesian form without technology. So here's the link we're making between polar form and Cartesian form. So we have root 2 cis of pi on 3, and then we go, well, what does that mean? What does cis mean? What's it short for? It's short for cos pi on 3 plus I sine of pi on 3. All right, remember we're bringing those things together in cis, so now we're separating them out. Cos of pi on 3 is half, so we're going to have root 2 times half plus I times root 3 on 2, and then we will just distribute the root 2 into the bracket, found it in Cartesian form, root 2 on 2 plus I root 6 on 2. Alright, so that's polar form. We've got in there 4C1, 4C2, 4C3, where we're reflecting on polar form. So let's move on to the next one. We've got some properties of cis, and there's a number of these. We have here 2 cis pi on 6 multiplied by 5 cis pi on 2. Alright. So the 2 and the 5 are going to multiply together. We have 10, and then we're going to have the sum of the angles, the arguments inside. All right, so that's what that collects to. So if we have cis theta times cis phi, it becomes cis of theta plus phi. That's the property we're using here. And so they're all listed in your notebooks, right? So if we want to add those together, we need them to have the same denominator. So we'll have pi on 6 plus 3 pi on 6. That gives us 10 cis of 4 pi on 6. And we'll simplify 2 pi on 3, I suppose. Now, you'll notice we've got 4c. We don't have 4d, and that's because it's Euler's theorem, which is no longer part of the course. You can find that in the subject outline, so we don't need to address that. It used to be. So then we move on to 4e, where we have De Moivre's theorem, and let's get straight into the application of that. We have 1 plus I root 3 to the power of 7, and it says find the exact value of this, the exact value of this complex number. Well, first let's convert that to polar form. 1 plus I root 3. So if you might remember, you might be able to do that in your head, all right, from complex numbers, but I'll make an argument as to why I'm going to write it like this. So firstly, when I think of the modulus of it, it's going to be the square root of 1 squared plus root 3 squared. Okay, so that's what, 1 plus 3, which is the square root of 4, which is 2. All right, so it has a modulus of 2. And then when we think of the argument of it, all right, again, we can chuck that in a calculator to determine the argument. But let's think about it in terms of the unit circle. We have it going across 1 and up root 3. Across 1 and up root 3. So if we want to know the angle, tan of root 3, O on A, tan of O on A, is going to be pi on 3. So what we've got here then, this complex number is 2 cis of pi on 3. And so you might be able to look at that and see that's what it is. All right, or we can just put this in our calculator as well. And I'm thinking if you put this in your calculator, it's going to generate the exact value of it anyway. All right, nonetheless, let's show the working out for it. So what does it become? If we use De Moivre's theorem, it becomes 2 to the power of 7, cis of, and it becomes 7 multiplied by pi on 3. That's what De Moivre's theorem says. Okay, that power goes there, and it goes in front of the angle. We multiply the angle of the argument by power of n. 2 to the 7, 128 is it? 128 cis, and we've got 7 pi on 3. So 7 pi on 3. All right, so again, we can rely on our calculator there a bit, but here's what I'd be thinking. I'd be going 7 pi on 3. That's 6 pi on 3 plus pi on 3, right? So that's 2 pi. All right, so we can eliminate that, and so it's just at its original position. It's still here. It's just going to be elongated a fair bit more. Rather than n2, we've got 128, right? And so we've got pi on 3, and let's convert that now. So we've got 128 times, well, cos of pi, 7 pi on 3, cos of pi on 3 is half, and sine of 7 pi on 3 is root 3 on 2. And then we can distribute the 128, so what's that, 64 plus 64 root 3 pi. Roots of complex numbers in 4f. And these are the nth roots of unity and so forth. So we've got, find the roots of z to the 3 equals minus 1 and plot on the Cartesian on the argument plane. Z to the 3 equals minus 1. So the first thing we need to do is we need to express minus 1 as in polar form. So where's minus 1? It's here. All right. The modulus of it is 1. All right. So yeah, we'll just write the modulus is 1, and the argument is positive pi. Okay, positive pi. So what we have is z to the 3 equals cis of pi. Z to the 3 equals cis of pi. So then when we cube root both sides, right, we're going to get z equals cis of pi plus k2 pi to the power of a third, 4k equals 0, 1, or 2. We have 3 possible solutions. And then we're applying De Moivre's theorem. Okay, so the third, 1 to the power of third is 1, so nothing's happening out front here. But we have the whole thing here multiplied by a third. For k is 0, 1, 2, and then we'll apply it. So when k is 0, we'll we'll have cis of pi on 3. When k is 1, we'll have cis of pi. And when k is 2, we'll have cis of 5 pi. We plot them on the Argand diagram. 1, 3, pi, 5, 1, Z2. Alright, so that concludes the chapter in the textbook. I remember we had to supplement it with a number of different worksheets on loci in the complex plane. So, let's do one of the questions around that. Sketch the locus such that the modulus of z plus 3 equals 2 times the modulus of z take by. Now, I think what we might do, because we're trying to look at some more simple ones rather than complex ones to begin with, it's probably best for us to let's just eliminate the 2 out the front. And we can come back and do that one if you want a bit later, but for now let's just focus on this. Alright, just so that we can understand what these questions are talking about here. Alright, so if we think of that, right, let's just think of it geometrically first, okay? If we have the complex number z plus 3, then its point of origin is not from here, but from the point minus 3, right? It has a horizontal translation of across 3 units. So that's where the first complex number is starting. And then the second one we have is z take I. So it has it's been shifted up 1 unit. So that's its original starting point. So positive 1. Okay? Now what we have is the modulus of the complex numbers drawn from these 2 points are equal. Okay, so what that means is if we're going to draw a complex number in this direction and in this direction, that's where they'll meet. Okay? If it's going to go in this direction and this direction, for the modulus to be equal, this is where they're going to meet. In fact, they're going to meet along a line that's exactly halfway between them. Right? So we can sketch that. And for this point, okay, everywhere along here, the modulus of them is always equal to one another. Okay? Because the distance from there to this line is always equal for those 2 points. So we can sketch it like that, we can understand it like that. But we can also determine the Cartesian formula. And I'm going to show you how we did it initially, but you may see a shorter way to do it. And the reason I'm going to do it this long way is because this is how you would do it when we're finding loci as such with a circle. Alright, so we go, what's z as a complex number? It is x plus iy, or you can go a plus b, doesn't really matter. So we've got z is some x plus iy, we don't know, and then we've got plus 3, and over here the same. Alright, and then we express both, we calculate the modulus of both, right? So the modulus means the square root of the horizontal component, which is x plus 3 squared, plus the imaginary component, okay, and that's going to equal the square root of, you will have x squared plus, we'll have y take 1 for the imaginary component. And then it's just a matter of expanding and solving this equation. Alright, now this is going to be the equation of the line for us. Where it would be different is if we had the number out the front. It does get a bit more complex because we do need to complete the square. For now, let's just focus on this process. Okay, so we'll get rid of the square root of both sides, we'll square both sides, and we'll fully expand. Alright, and probably what we want to do, like equation of a line, we want to isolate y, right? Let's get y by itself. Straight away what we can see is we've got x squared on both sides, we've got y squared on both sides, and then we're just left with y over here, and so we just get y all by itself. So first thing, we take 1 from both sides, so I'm going to have 6x plus 8 equals minus 2y, and then we'll divide both sides by minus 2. So we'll have y is equal to minus 3x take 4. Alright, and that's going to be the equation of that line. Okay, So I think that's a pretty good recap of complex numbers. So yeah, encourage you to, again, have a look over the textbook, have a look over the revision guide. Yeah, let's spend some time doing some complex numbers.